Hi everyone, thanks for coming to the tutorial. I'm Shubham. I want to talk about object-centric physical and spatial inference, and in particular I'll focus on how using graph-structured neural networks can let us really infer accurately the physical and spatial structure of scenes from images. And just as a motivating example, let's consider this particular RGB image shown here. And let's imagine that there's a robot or an agent that is seeing the world and observing this image. Now, in fact, when this agent observes this image, what it's really seeing is just one glimpse or one perspective of the underlying physical and spatial world. So for example, from context of this particular robot shown here, it's just seeing the underlying 3D physical world from this particular perspective, and it's trying to decide how it should act, what it should do, etc., from just this one image. And so with that in mind, let's just consider what sort of a representation should this agent infer from this image that it sees. Now, there are many possible answers that have been explored in the computer vision literature sort of over the many decades. But one more popular answer these days is we can take a neural network, let's say our favorite ResNet, and infer a single latent variable, sort of a high dimensional latent vector that represent this image implicitly. For example, we can take our favorite ResNet and get a 1024 dimensional representation of whatever we are seeing here. Now, while this is very good for certain tasks such as scene classification, it really misses the compositional structure of the scene. For example, we know that in this particular image, there's a couch to the left, there's a chair further ahead, there are some more chairs to the right. We also understand the 3D structure of each of them. And so having a single latent variable does not really respect the compositionality of this particular scene. And as soon as I say that, one might think that, well, instead of trying to represent the scene as a whole, let's just infer a per component representation. So for example, let's consider these three components highlighted, for example, the blue couch, the orange chair, and the black table, and infer a per component representation. And this can actually give us far more accurate details at a particular component level. For example, given such a representation, we can then, let's say, even decode the 3D shape or location of each of these components. But what this misses is the relationship amongst these components. We're reasoning about or representing each of these components independently and not really taking into account what these components are together. For example, this misses the fact that there is a pillow on the couch, or that there is a cup on the table, or that, for example, the table is in front of the couch. And in fact, a lot of the times, the relationships between different objects or different components in a scene are what's interesting. So just to show an example here, when we are seeing this particular image, if we just think about isolated components, then we'll say that this particular scene has a sheep, a couch, and a trampoline, etc. And each of these components on their own are not that interesting or not that surprising. What's really unique about this particular image, or in this case, this particular video, is the interaction amongst these components. That there's this one object, a sheep, there's this other object, a trampoline, and they're interacting in a novel way. The relationship between these two in this particular video is what's interesting to us, and also interesting to this particular little girl who probably has seen sheep before, who probably has seen trampolines before, but it's just the relationship or the interaction between these different components that's really interesting. And beyond just our desire to capture all the interesting things, being able to capture the relationships is very fundamental and critical towards several tasks that we want to solve. So given this image, for a robot that wants to manipulate this scene, it really needs to understand that the cups are stacked on top of each other. Or sort of a similar example, for this robot from MIT that plays Jenga, it really needs to understand how the blocks are stacked on top of each other to be able to figure out what the effect of removing a particular block will be. Or for example, this tennis player needs to understand the relationship between his racket and the ball to be able to figure out how he should act to change the scene or sort of return the ball in this particular case. And with this in mind, the approach we'll propose is actually just a very simple change in addition to the compositional representation we talked of earlier, which is in addition to representing each of the components of the scene, we'll also represent the relationships amongst them. That is, not only will we have a per component representation, we'll also capture the relationships among them. And what I want to show today is how just this very simple idea the representation of a scene in terms of the components and the relationships will allow us to perform tasks related to spatial and physical inference. Sort of more concretely, be able to predict 3D from images and be able to predict the physical representation and how the world changes, let's say, as a robot acts. And I want to begin by focusing on the latter in a very, very simple scenario. So let's just consider this RGB image shown on the left and try to imagine what the future of the scene will be like. Now, we all understand that this particular configuration is unstable, that the blue block and the yellow block will fall down because they're placed very close to the edge of the pink block. And so, here is how the scene evolves, and this is akin to what we were all anticipating. And the reason why we humans can sort of infer this future motion from just the single image I had shown earlier is because we understand this particular scene depicted in terms of the different components. We understand that the scene is comprised of different objects, or what I'm calling here entities, and that each of these will move, but that their movements will be correlated. For example, the way the yellow block will move sort of depends on the blue block and vice versa, and both of these will kind of fall down together in a constrained manner. And so we wanted to have an approach that leverages both these insights, that any scene that we see is really composed of these entities that move in a coherent manner. And towards this, the high-level idea is actually very similar to what we discussed earlier. That is, we should be able to represent a scene in terms of the different components while accounting for the relationships between them, sort of using a graph neural network. So given this input image, what we do is infer this compositional representation. And then while accounting for the relationships between these different objects or these different entities, we sort of predict the future in this implicit representation, in this compositional representation. And sort of once we have done that, we can then go back to the pixel space using a decoder which takes this compositional representation and tries to construct back the frame. And I'll go into the detail of both of these components in a bit. But what I want to highlight is that this approach is also related to a couple of lines of work in computer vision. For example, there have been many papers which try to predict the future pixels given a single or multiple images, and they do so by factorizing sort of similar to what I'm going to show. However, the factorization typically involves only a foreground and a background. So if you think there's just a single node corresponding to a foreground and not really a graph-based decomposition of the different entities present. On the other hand, there are these several approaches which try to learn intuitive physics, where the representation is a bit more similar to the one that I'll talk about. But all of these have been examined in a setting where the input is not an image, but more of a state space, that there are these different balls whose 2D locations are known. We are only interested in inferring future 2D locations and not really interested in inferring the pixels. And so what I want to present, in some sense, combines or ties in some of the insights from both of these lines of work to be able to predict the future pixels given an input image. So as I mentioned, our prediction approach takes this input image, infers a representation, predicts the future, and then decodes it back. And let's just look at each of these components in a bit more detail. So concretely, given this input image, what we infer is a per entity explicit location and a per entity implicit feature. So sort of concretely, for each of the objects or the entities, we represent it by a 2D location in form of a bounding box around that entity, and also an implicit feature for each of them, which is obtained by just encoding the image patch around that entity. And if you think of it, this implicit feature should be able to capture things like color and shape, etc., whereas the location, in some sense, captures the configuration of the scene. And then our initial graph essentially connects all these entities to each other, where at each node of the graph, the feature is this composition of the per entity location and the per entity implicit feature. Now, given this representation, the role of the predictor is actually pretty simple. Given the current configuration, which is x at time t, it wants to predict the future representation, which is x at time t plus 1 for each of the entities. And the way it does so is by using graph networks to account for the relationships, to account for the local interactions between all these entities. Sort of more formally, for each edge, we compute a per edge feature using the features of the two entities on that edge, and then update the feature of each of these objects or entities using its own feature as well as the features of all the incidental edges. And here I'm just showing sort of a one-step message passing, but actually in practice, there are multiple steps of message passing when we go from the representation at time t to time t plus 1. And in fact, we don't need to apply this predictor just once, but in fact, we can apply this predictor sort of consecutively and recursively. So given the current configuration at, let's say, frame equals 0, we can predict the configuration at frame equals 30 by applying this predictor recursively 30 times. And so given this representation, we can recursively apply the predictor to get a future prediction, let's say 1 second away or 30 frames away. And then given that representation, we just decode it to obtain the pixels in the image. And I'll maybe skip some of the details of the decoder as it's a bit orthogonal to the tutorial topic, but essentially given the 2D locations of each of these entities, we paste a feature at that location and then decode by sort of implicitly accounting for occlusions, etc. And I'll skip some of the details and analysis of this decoder, but sort of suffice it to say that given this compositional representation, if we represent the location a bit explicitly, then we can get sort of more accurate decodings. And so, given this framework, again, where we had a very simple 3-stage process, the encoder that goes to a semi-implicit representation of each entity, and a predictor which really accounts for the relationships between them to predict the future, and a decoder which gives us back the pixels in the image. And we did so by accounting for the relationships and the compositional structure of the scene. And so one might ask, was this really important? Was it important to reason about the relationships among entities, or to even decompose the scene into different entities? And to do that, we compared our approach to certain baselines. For example, sort of what I'm calling a no-edge baseline, where we ignore the relationships among entities. In some sense, the predictor predicts the future for each entity independently. Or for example, a no factorization baseline, similar to some of the foreground-background separation methods that I was talking about earlier, which don't factor out the entities, don't respect the compositional structure, just represent the scene as a single high-level variable and predict the future in that high-level latent variable. And here's just a representative video showing the initial frame on the left, and the predictions of various approaches on the right. And we see that our approach, which A has a compositional representation and B accounts for the relationships among entities, does a better job at predicting the future. And we also empirically verified this using sort of a perceptual error, where in this graph lower is better, and we see that sort of the blue line, which is ours, gives us a lower perceptual error. But of course, as we make predictions for longer time steps, the error obviously increases, but accounting for the relationships and the compositional structure really gives us gains, both in the pixel generation metric, as well as in terms of the predicted locations of each of these entities in pixel space. And sort of one benefit of using this graph-based compositional approach is we get generalization for free to some extent. So we trained our system using only 3 blocks, but we can test it in settings where there are more blocks used. So for example, here we're showing some results in settings with sort of 4 to 6 blocks, even though we trained it on 3 blocks. And we see that the predictions that we get are sort of pretty meaningful. And what I showed earlier was just prediction in this setting where there are these synthetic shapes that are falling down. But the exact same idea, that we should have a compositional representation where the predictor accounts for the relationship among entities, also generalizes to other domains, such as predicting motions of humans, in which case the human joints actually serve as entities, and we can have a skeleton of human as the dependency graph between these different entities. And so the exact same framework as I described here applies to this setting as well, where we can then predict the future motion of the human. Or for example, in the image shown here, we can predict that after certain frames, the human would have moved up while sort of doing this more athletic activity. And we also have results in the paper and comparisons to sort of various baselines, and I'll skip over some of the details here, but you can look them up in the paper later. And sort of move over to a bit more active setting. So what we saw so far was just this passive prediction setting. That is, how will the scene change on its own, assuming there's no robot that's interacting with the scene. Instead, what's important for a robot to also know is, how will the scene change if that robot acts? If it pushes a certain block, how will the scene change? And just to maybe convince you a bit more about the need for an active prediction, I want to highlight one specific task, which is, let's say we have a current observed configuration of a table. In this case, there are these two blocks lying on a table, and we have a certain goal configuration. That is, you want to move the blue block around the red one without disturbing the red one. And in this case, there's just a robot who can only push the objects around, and it wants to figure out what sequence of actions it can take to be able to sort of achieve this desired goal from this current configuration that it's observing. And the reason we need active prediction is because this very long line of work in sort of control literature called model predictive control, which allows us to perform this task if we have access to a forward model. So concretely, what model predictive control requires is, given a current and a goal observation, we need to have some embedding of both the current and goal states. And given this embedding, we need to have a forward model that sort of predicts the effect of robots' actions given the current observation. And what the model predictive framework allows us to do is search over many possible action sequences and then select the best one. Sort of more formally, we plan for a certain horizon. In this case, 3 steps. That is, we explore many random action sequences of length 3, and then choose the best one that leads us closest to the goal, and then sort of execute the first action and then repeat this procedure. And to be able to instantiate this model predictive control framework, all we need to do is instantiate this forward model that takes in a current configuration and, given a particular action that the robot is trying to take, hallucinate what the future configuration will be. And again, there have been several prior works which address this question of what the forward model should be. And in particular, they often use explicit representations of the state, such as the physical mass of the object, the location, the friction, etc. Or, for example, a fully implicit representation, just a high-level code which does not respect the compositional structure of the particular scene. And what we instead propose to do is use a representation similar to the one I described earlier, which is this compositional representation which respects the relationships between entities, and in this case also the robot, to infer the future configuration of the scene given a particular action. So just looking into it in a bit more detail, we have the semi-implicit representation, which, similar to earlier, has a per entity location and a per entity sort of implicit feature which can capture things like its color or shape, etc. And then for a predictor, its job is again to be able to predict the future configuration given the current configuration and the action AT that the robot takes. And the way it does so is similar to before, by instantiating a graph, where in this case the nodes of the graph are the objects as well as the robot gripper, sort of where it originally is and how much it is moving, and predict the future configuration of the scene by modeling the interactions sort of implicitly using this graph neural network. And once we do that, we sort of get this future state configuration prediction, and we can instantiate this model predictive control framework using this compositional forward model. And sort of one additional nice thing is that we can just train this forward model using lots of random interactions. So in this particular work, what we did was took a robot, placed many blocks on a table, and let the robot interact randomly. So here I'm just showing some sample random pushes that the robot does. Sort of actually did sort of 5,000 random pushes and observed how the world was changing as a consequence of each of those pushes, and learned a forward model using just these random interactions. And what this then allows us to do is sort of instantiate the model predictive control framework to go from initial to goal configurations. And before I show our results, I just want to highlight sort of a result from a baseline method that does not represent the compositional graph-based structure of the scene, but instead just tries to predict the motion in pixel space. And sort of for long-range motions, we see that this does not perform well at all. Whereas our approach using this compositional forward model does a far better job at being able to sort of change the scene or the robot actions. I mean, here you're seeing at the end the robot is doing some spurious actions because it already achieved the goal, but sort of it does so more robustly than the baseline, which does not use the compositional nature of the task. And here are just some more results in real as well as synthetic settings on the right. And again, we see that our approach does a better job at achieving these relatively long distance goals and planning action sequences that can lead us to these goals. Yeah, here are just some more videos. And so what I talked about so far were reasoning about these interactions in a physical sense, but these interactions were restricted to be sort of contact interactions, explicit contact interactions, where one block is on top of each other or touching the other one, or if the robot is pushing a particular block. But sometimes these relations are also a bit more subtle. For example, if I show you this particular configuration, where there's a chair sort of near a table, versus this particular configuration where the table is exactly in front of a chair, we recognize that there is some fundamental difference between the two, that in one case, the second case, the configuration is a bit more amenable to us sitting down and working on the table while sitting on the chair. So we also wanted to look at these more implicit forms of relations, or relations as configuration priors, that given these two different objects, what are plausible configurations amongst them. And what this can really help us with is infer a 3D structure of a scene. For example, given this image shown on the left, to be able to infer this sort of a representation where we have a 3D structure of the entire scene, of the table, of all the chairs in it. Being able to model the relationships between all the objects is really critical towards sort of being able to do this accurately. So formally, what we want to do is, given a single input image, we want to be able to infer a 3D representation for each of the objects. That is, we want to infer the shape and pose for each of the objects in a scene. So concretely, the representation infers for each object a translation, a rotation, and scale, and also sort of a volumetric representation that depicts the shape of this particular object. Now, what prior approaches often did is they respected the fact that there are these different components, but they ignored the relationships amongst them. So they would predict the pose and shape for each of the objects independently. So for example, for this chair, they would take the blue patch highlighted here and predict the particular 3D representation. For the table, just take this patch highlighted here, predict the 3D representation. And again, this ignores the fact that this chair is just behind the table. And so these representations should sort of be related. So instead, what we do is also reason about the relationships among these objects. And given this image, predict not just sort of a unary estimate of where these objects are, but also predict an inter-object pose, which is where, given this image, do I think where is the table with respect to the chair? And given these initial unary and binary estimates, we can then combine them to get better and more informed estimates of the 3D shape and pose of each of the objects. And so going into this in a bit more detail, again, on the left, we have these initial unary pose estimates and relative pose estimates. And we wanted to be able to compute these global pose estimates. And the way we can do this is essentially, least square optimization. So we have estimate of where the object A is, where the object B is, and where they both are with respect to each other. And essentially the optimal location of A and B sort of corresponds to this least square minimization problem, which I'm not going to sort of go into too much detail here, but sort of given these unary and relative estimates, we can compute a translation for each of the object that best explains both of these predictions. And so all you should take away from this is that this is a very explicit or a specific kind of message passing system. That is, given sort of the predictions of these two different nodes, whereas graph neural networks do this more implicit form of message passing, here we are doing a much more explicit form of message passing, where we are updating the location of each of these nodes based on this explicit relative pose message that we are passing. And this allows us to sort of update the configuration that we predict and get better 3D estimates. And just as an illustration, given this particular image, this is what a previous work, which does not account for relationships, predict. And we see that the configuration is a bit off. The chair is not really behind the table, whereas our approach, which also reasons about the relationships, does a much better job at predicting the scene configuration. And here's just a similar result for a different scene. We see that the table with respect to the couch is a bit off, but if we incorporate relative prediction as well, this improves significantly. And sort of while I earlier showed this more explicit form of message passing, we can also have a more implicit form of message passing, which is similar to ones you were seeing earlier. Just use a graph neural network, for example, a GCN, where we have a per node representation. We can do some implicit message passing and then infer a per entity sort of pose and shape. And we can also not necessarily use a graph convolutional network, but use something like an interaction network, which again does this implicit message passing, but in a slightly different way. And again, have a per entity inferred spatial location and a shape. And in this particular case, because the task we are interested in is this very explicit representation, we found that it's a bit better to use this more explicit message passing as opposed to an implicit message passing. So at the top is this sort of baseline where we don't have any kind of relationship reasoning, and the other three are methods with some implicit or explicit relationship reasoning. And sort of the takeaways are that A, having any form of relationship reasoning helps significantly, but that for this particular task, being more explicit about the kinds of messages being passed helps even more because sort of the nature of the specific task that you're interested in. And here I'm just showing results using this MAP metric where sort of higher is better. And with that, I'd just like to highlight again that there was this essentially very simple idea that we saw today, that given this scene, we should infer a compositional representation where we respect the relationship among the different components. And this allowed us to sort of make more accurate physical and spatial inference. And I hope that convinces you that this is sort of the right way to go when we are pursuing any sort of spatial or physical representations, to have a compositional representation and really reason about how the components interact with each other. Yeah, with that, I'll stop and be happy to take questions.